Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about conservative and non-conservative forces. This is not a political discussion. This is a physics discussion and an important one. To get at the heart of the matter, I want you to consider the following very simple experiment, which you could even try at home. Imagine that you've got a copy of your Wolfson textbook on a table and you started off with some initial velocity traveling to the left, and then a short while later, the book is at rest on this horizontal table. And I'd like to analyze this situation just using the energy principle. So we're going to write down the energy principle that says that the change in the energy of the system is just given by the work done on the system by its surroundings. And in this case, I'm going to assume that the system is isolated. I've drawn a horizontal line around a horizontal circle around the system, and there's no interaction with the system. Gravity is not important because the book is not changing its elevation. So in this particular case, it's an isolated system. We don't expect the energy of the system to change. And yet, in the initial state of the system, the book has some kinetic energy, and in the final state, the speed of the book is zero, so it has no kinetic energy. So the question is, the kinetic energy uh, has decreased between the initial and the final state. There's no change in the potential energy due to gravity. Where did that energy go? That's the question, and I bet you a lot of you know the answer. The answer is that the book, in coming to a stop, heated up um, things in the world a little bit. There was friction, and the what was initially kinetic energy in the book uh, ended up in the form of heat. And if you don't believe me that this is true, just try rubbing your hands together, and and you'll feel that transforming kinetic energy into heat. So this suggests that we really need to broaden our definition of the energy of the system. Previously, we had considered just potential energy and kinetic energy as the types of energy in the system. Now we want to include this new form of energy, which is heat energy, and it's traditional to use the letter Q to denote energy. So with this broader definition, we can still maintain the idea that if you have an isolated system, you don't expect the total energy of the system to change. And this is sort of a general trend of what physicists like to do. We're very fond of this idea of conservation of energy for an isolated system. And whenever we're in danger of seeing it violated, we just look very carefully and find that the energy has gone into a different form. Now, I just a word of caution. While I generally admire Richard Wolfson a lot, and I like his textbook a lot, I don't quite like what he says on this score. He does his accounting a little bit differently. And as I keep saying, energy, there's a lot of accounting, and people can disagree on the rules of accounting. But Wolfson's language is a little bit disconcerting here. He says that in this case, he would describe it as energy is not being conserved because friction is a non-conservative force. And I understand where that comes from. In fact, I'm going to tell you what I think we mean by non-conservative forces, and I agree that friction is a non-conservative force, but I prefer to say that heat is another form of energy, and if you broaden your definition of energy, even though there's friction in our isolated system, the total energy of the system is conserved. Okay, so let's start by talking about conservative forces. And the best way to tell you what I mean by a conservative force is an example. So I would say, everyone would say, that gravity is an example of a conservative force. So what do we mean by that? Well, I refer you to this convince your neighbor problem that we've talked about, and everybody was able to say that if we start a ball at rest at the top of the track, at the top here, a height h above the bottom, and we compare what the speed of the ball will be for different tracks, and if there's no friction anywhere, the ball is just rolling down these tracks, we all agreed that the ball would end up with the same speed regardless of the color of the track. So the correct answer in this convince your neighbor was E, the speeds are the same for all the tracks. And we could explain that by saying that the potential energy due to gravity, which we defined, or change, I should be careful, changes in the potential energy due to gravity are defined as minus the work done by gravity in moving from an initial configuration to a final configuration. And we argued that, gravity, as the ball falls down the track, gravity is going to end up doing positive work. It's tending to speed up the ball, and the amount of work that gravity does is mgh. And with this minus sign, therefore, we get that the change in the potential energy due to gravity is minus mgh, independent of the particular path that was taken by the ball. And that's a general characteristic of gravity. When you calculate the work done by gravity between some initial place and some final place, the result that you get doesn't depend on the particular path that was taken by gravity. So we say that the work done by gravity is path independent. Path independent. And if you think about it, that's really, in order for making use of this approach of defining a potential energy to make any sense, the work done really does have to be path independent, because otherwise it wouldn't make sense to talk about the potential energy that the ball has at the top of the track. Because if the changes in potential energy depended on how you got to the bottom, then we wouldn't be able to talk about what the potential energy was at the bottom of the track. So an essential feature of a force like gravity is that when you calculate the work done by it, it is path independent, and that enables us to define a potential energy associated with it. And we say that such a force, where we can define a potential energy and where the work done by the force is path independent, we call such a force a conservative force. And other conservative forces that, well, there's one other one that we've encountered that is important so far, and the spring force is also a conservative force. Spring force is also a conservative force. And to convince you of the truth of that statement, I'll just draw a little picture here. And if you have a mass on a spring, and you have some coordinate system with a 0 and some initial position and some final position, then the work done by the spring on the mass only depends on where you start off and where you end up. And it doesn't matter, you could go back and forth several times. It doesn't matter. All it depends on the work done by the net work done by the force only depends on where you start off and where you end up. And for that reason, the work done is path independent. And we can define a potential energy associated with the spring, which we've already done, which is equal to 1/2 kx squared. Okay, and now to talk about non-conservative forces, the best way to do that is again by an example. And the example, I want to take the same example of these tracks, but imagine that the tracks are the thing that's sliding down, the tracks are rough, and the thing slides down, and as it slides down, there's a frictional force that acts on the object that's sliding down the tracks in addition to the gravitational force. And what you find then is that the amount of work done by the frictional force will very much depend on the particular path that you take to get between the starting point and the ending point. So if you have a direct line, there might be less work done by friction than if you have a very long path. Uh, and so the work done by friction is path independent. The work done by friction is path dependent. And that means that it really doesn't even make sense to define a um, potential energy associated with friction. So there is no potential energy associated with friction. So what do we do if there's a problem where there's frictional forces present and we want to use our energy principle to solve the problem? What do we do? Well, again, the best way to show you is with an example. So here's the example I want to consider. It consists of objects sliding on a track, and the track is frictionless for the most part until it gets to this section here. And in the story, the block starts off with an initial velocity pointed to the right with a magnitude of 6.0 meters per second. It goes down this dip and back up and rises to an elevation h. Uh, of 1.1 meters above where it started out. And then it hits this rough patch of track. And this track is characterized by a coefficient of kinetic friction with a value of 0.6. And it's observed that the block comes to a rest some distance d after it entered the rough patch. And the question is asking us to find d. So can we do that? Of course we can. Let's show you how. Now, the secret, as is usually the case, is to be systematic in your accounting and careful about how you define your system. So here's how I am going to choose to do my accounting in this problem. I'm going to define my system to include, first of all, the Earth is going to be part of my system because we're going to have a potential energy due to gravity. So I'm going to include the Earth, but I am not going to include, and I'm going to include the block, obviously, no matter where it goes, but I am not going to include this particular rough patch here. This part here is never going to be part of my system. That's going to be part of the surroundings. So the rough patch here are part of the surroundings. And I claim that with this definition, well, it's always true uh, that we're going to be able to write down the energy principle. And the change in the energy of my system is just going to be given by the work done on the system by the surroundings. And so by defining things this way, I've sort of finessed the issue. I've included, because I knew friction was a non-conservative force, I just dealt with that by making the frictional force part of the work done by the surroundings and not including it in my system. Now, there are other ways to do this problem, but this is the way that I am choosing to do it because I think it is the simplest. And I can write on the right-hand side, the frictional force is going to do work on the block, and it's going to be negative work, of course, because friction is in the direction opposite to the displacement, and the magnitude of that work is just the magnitude of the frictional force times the displacement, which we're calling d, and again, the minus sign out in front just says that the work done by friction is going to be a negative quantity. So that's the right-hand side of my equation there. And then on the left-hand side, the change in the energy of the system, I can write this as the change in the potential energy of the system plus the change in the kinetic energy of the system. Okay, well, the change in the potential energy of the system, the block rises by a elevation h in this problem. So the potential energy of the system is plus mgh, and we'll plug in numbers in a minute. And the change in the kinetic energy of the system is it starts off with a kinetic energy of 1/2 mv naught squared, and then it ends up with a final kinetic energy of 0. So the change in the kinetic energy of the system is minus 1/2 mv naught squared. And I'm just going to remind you that our model of kinetic friction says that the frictional force has a magnitude of mu k times the magnitude of the normal force, which in this case is going to work out to be mg, and then I have my factor of d here. So this is the equation that we're going to make use of, this equation here, and notice that we know well, we don't have to know the mass, it turns out, because every term in this equation has a factor of m in it, so we can just divide by m and get rid of that. And then everything else in this equation, other than d, we are given in the problem, so we can just solve for d. So the problem is essentially over. It's just a little bit of algebra and plugging in. That's all that remains. So just rearranging this equation and solving for d, I hope I did the algebra right. I get that d should be equal to this quantity, and then we're going to plug in the given values. We have divided by 2 minus 9.8 meters per second squared times h is 1.1 meters divided by mu k, which is 0.6 times g, which is 9.8 meters per second squared. So plugging that into my calculator, I find that d is equal to 0.14 meters, although you should definitely check me on that. I don't absolutely guarantee that I did that right, but I think I did. Okay, so that's it for this What's the Big Idea on conservative and non-conservative forces, which also included as a bonus this particular worked example. So hope to see you again soon. Bye bye.